Hi, welcome to Unit 9, Day 5, 9A, Day 5. Today we're going to look at arcs and chords and how they can relate to each other in a circle. So we need to remember that a chord is a segment with endpoints on the circle. If the chord is a diameter, then it divides the circle into two semicircles. So when it goes through the center as a chord, we call it a diameter, and I can see that half the circle is on one side of that diameter and the other half is on the other, and we have two semicircles. If my chord is not a diameter, so it just has its endpoints on the edge of the circle, and it does not go through the center, then we're going to end up with a minor arc that's going to be less than half the circle, and a major arc that's going to be more than half the circle. Okay? When we have congruent chords in a circle, or congruent arcs in a circle, if we have the same circle or congruent circles, if they have the same radius, then two minor arcs are always going to be congruent if and only if the chords are congruent. So the minor arcs are congruent if the chords are congruent. So when I look back, I can see that because of the tick marks, I know that segment AB, which is a chord because its endpoints are on the circle, and segment CD, I can see that they have the same length because of the tick marks. They're both chords. Because they have the same length and they're in the same circle, the intercepted arcs, so from one endpoint of the chord to the other endpoint of the chord, that's the intercepted arc, that arc is going to be the same as the arc that's intercepted by the other chord. So this arc here. So arc AB, that's this arc, is going to be congruent to arc CD, that's this arc. And that's only true if the segments that connect those ends of those arcs are both also equal. Okay, so let's look at some examples. My first example, example A, says to find the measure of arc XY. Okay, I can see that I do have congruent chords here and here. That means the arc that connects the endpoints are going to be congruent. So this arc is going to be congruent to this arc. And remember, if it says the measure of, then it wants the degrees of that arc. Arc length would be how long is it in inches or centimeters or whatever, but this says measure, so I want the degree measurement of that arc. Okay, so these two arcs, because the chords are congruent, these two arcs are congruent. So if one is 105 degrees, then the other one is also 105 degrees. Okay, when I look at the next one, I want to find how long is FG, that's this chord right here. And notice there's no notation above or in front of the FG, so it doesn't show that it's an arc, it doesn't show that it's a segment, it doesn't have a little M in front of it. If you just have the two letters, and we've talked about this before lots of times since Unit 1 is when we first did this, so way back in August, September. If you just have the two letters, that's asking for distance. How far is it from F to G? And it's always the straight line distance. So from F to G, I want to know how long that piece is. And I can see its intercepted arc has a tick mark on it. So that means this chord will match the arc that matches FG's arc. So I can see the tick mark, so this arc, and the chord that intercepts that arc has a length of 6, so that means FG also has a length of 6. And we don't know the units here, so I'm just going to say units. Okay? All right, the next thing we're going to talk about, the next property for today, is the perpendicular bisector of a chord is the diameter. So that sentence, let's break that down. We have the diameter of a circle is perpendicular to a chord, or the perpendicular bisector of a chord is a diameter. It's kind of converse ways to say it. So if the diameter of a circle is perpendicular to a chord, so two things are happening here, right? The first thing is it has to be a diameter, which means it has to include the center. And then the second thing is it has to be perpendicular to a chord. So remember, perpendicular, our symbol is the upside down T, and that means it intersects the chord at a 90-degree angle. Okay, so when I look, I can see if I'm looking at EG and I'm looking at FD, those are both chords, but the one that goes through the center, that is my diameter. So EG is the diameter, so that means the diameter, is bisecting, cutting in half equally, both the chord and the arc. So the diameter divides the chord into equal pieces, and it divides the intercepted arc of that chord into equal pieces. Okay, so again, it has to go through the center, it has to hit at a 90-degree angle, and if that's the case, then it's going to divide the chord in half, and it's going to divide the intercepted arc in half. And what's kind of cool is it divides both sides of it divides the minor arc in half, and it also divides the major arc back here in half. Okay, so you get two sets of equal arcs, and you get one set of equal segments. Let's look at some examples. We have 3 examples here from the same picture. Okay, so in circle P, here's circle P, in circle P, the radius is 13, so I know from Q to P is 13, and from P, if I were to extend out, it would be 13, or from P to S is 13, from P to R is 13. Okay? RS is 24, so RS all the way across is 24. The measure of arc RS, so from R to S, arc RS is 84 degrees. Find each measure. Okay, now remember my rule up here said it has to be a diameter and it needs to be perpendicular to a chord. So if I look at this picture right away, I don't see a diameter, right? Because this chord does not go through the center. My center's here, so that chord is not a diameter. And then this isn't a diameter because it's just a radius, right? So that one is not a diameter because it's just a radius. But I do know that the radius is part of a diameter. So if I were to extend that out, then I would have a diameter that would be perpendicular to a chord, and that I'm allowed to do. Okay, so this diameter that I can sketch into my picture using the radius is perpendicular to a chord. So that means it divides the chord in half, it divides this arc in half, and it divides the major arc in half. Okay, so using that information, I should be able to find all my other information. Okay, so I know originally that RS was 24, so this whole piece was 24, so now I know I've got 12, and I've got 12, because I know that's now been divided in half. The measure of arc RS was 84, so R to S was 84, so that means each side is going to be half of the 84, so 42 and 42, so that I get the other half. Now what about these halves? I don't think it's going to ask me about these, but let's talk about how we would find those. I know the whole circle has 360, right? So all the way around is 360. So I could take the 84 away from 360. If I do that, 360 minus 84 is going to tell me that this whole major arc here is 276. And then if I divide that in 2 for this piece and this piece, I get 138. So this piece here is 138, and this piece here is 138. Now, is that the only way I could have done that? No, not necessarily, because I could have also used the idea of, let me see, do I have something I can use this piece of paper, of a diameter, right? I could have said, oh, I drew in the diameter. I know there's 180 degrees in a semicircle on one side of a diameter. So I could have taken this 42 degrees and subtracted it from 180 to get 138. And then I know if this side's 138, this side is also 138. So that's kind of the neat thing about math, is there are more than one ways oftentimes to do a problem, and you'll still get the correct answer as long as you're using good math. Okay? All right, so now let's see if we can answer these questions. My first one says the distance from R to T. And I know it wants the distance because there's not an arc, there's not a segment bar, there's not a little m in front, there's not any symbols, right? So that means just the distance from R to T. So from R just to T, I can see that that distance is 12. The measure of arc RQ. So this time I know I'm looking for a degrees because it's the measure, and I know it's the arc RQ. So from R to Q, the arc, I can see that that is 42 degrees. And these, we don't know what kind of units they are, do we? 84, 24, nope. Okay, and then TS. TS, I can see that that is, T to S is going to be, if that is 12, that's going to be how long that piece is. Okay. Now, notice this also did tell me that the radius is 13, but I didn't need that for this problem. Okay. I know from P to Q is 13. I don't know how long this little piece is here because I don't know that this chord, what the relationship, how it divides that radius. So I don't have enough information to find that little piece there just by looking at it. But kind of a neat thing, and this is just a little extra information for you. You can draw a radius anywhere in the circle, and I know it's going to be 13. So let's say I wanted to find out how far it is from just T to P. I could draw in the radius here, and I know that this piece here is 13, and this piece here is 12, and I know this is a little right triangle. So I could use 13 for the radius, 12 for one leg, and then I'd want to find that other leg, and I would actually find out, this is what we call a Pythagorean Triple, where there's no decimals. I would find out this piece here was 5, which means this piece here would be 8, because the whole thing is 13. So kind of a neat, you can use all sorts of little extra information to find lots of things, because you can add, we know all the properties about all of our radii and diameters and chords. Okay, in the next video, we're going to look at congruent, how you can tell if two chords are congruent even if you don't know if they have the same intercepted arc. So come on back for that video.